Go. All right, so we're going to start on force today. This is just a lame attempt at a joke. If you look at this picture in one way, you see a bell. If you look at it the other way, you see a guy with no arms. I don't know, it's not that funny, but there it is. All right, so here's where the notes start. A force is a push or a pull that changes an object's state or motion because forces cause acceleration. So there are two states of motion that an object can be in. It can be at rest, which is zero velocity. Or an object can be at cruise control, which is some speed, right? A force comes along and causes that object to change its state. In other words, it causes the object to accelerate. Force is required for an object to accelerate. If an object doesn't have a force applied to it, or an unbalanced force I should say, then it will not accelerate. According to Newton's first law, if you're at rest and no unbalanced force is applied to you, you'll stay at rest. And if you're in motion, if you're on cruise control and there are no forces applied to you, you will stay at cruise control. And we're going to see that in a minute. But that's what this is basically saying. Forces cause acceleration, which acceleration by definition is a change in its motion. A change in motion. That's acceleration. All right, moving on. Examples. There are lots of examples. The ones we will focus most on are these. Gravity, which you already talked about. Gravity causes weight. And then the other ones we will focus most on are friction, tension, and the normal force. Forces are measured in newtons. So the four that we will work mostly with here is gravity and subsequently weight, friction, tension, and the normal force. Strong and weak nuclear forces are a chemistry thing, and we will touch briefly on electromagnetic forces in our wave unit. Okay, so those are the ones that I want you to get mostly. Gravity, friction, tension, and normal. All right, next slide. So, this is big. Force is yet another vector. We've been focusing on vectors since the beginning. It's been on both tests that we've done. Right? We started out with the vector velocity, added another time to that, and now we have acceleration. And we're going to apply a force in a certain direction, which will cause a change in the motion in the same direction. So force is another number that requires two things. It requires magnitude and direction. We will represent forces with an arrow. The size of the arrow, how big or small the actual arrow is, from tail to tip, will represent the magnitude. So the bigger the arrow, the bigger the magnitude, the harder something is being pushed or pulled. And then the direction of the arrow is the direction of the force. So for example, here I have a dam that a force is being applied to the dam, or the dam is applying a force to the water that's keeping the water from flowing through the dam. Forces that keep things from falling through or support things are called normal forces. For example, everything on top of this desk is being supported by the desk. So the desk is exerting a normal force on them. If I lean up against this board right here, I'm not going to fall through it because it supports my weight with a normal force, a normal supporting force. The dam is supporting the weight of the water, which is keeping the water from flowing through. So it's a force. The small n, the subscript n, represents the type of force that it is. So the subscript n because it's a normal force. So then what we end up with is a damn effing force. Right, because it's a damn and it's Fn, damn effing force. Come on, that was supposed to be funny. It's a damn effing force. Are y'all not awake yet? See, that's I'm not cursing because it's an actual damn and there's an actual F and it's in, but it's damn effing. Fn. Okay, I'm not even going to try to explain it anymore. All right, you either get it or you don't at this point. All right, so we're going to go through these very quickly. Aristotle, first guy that attempted to talk about what causes motion. He said there are two kinds of motion, natural motion and forced motion. The things that cause natural motion are the natural things. The earth, the wind, the fire, and water. And all other motion is caused by force motion, by something forcing it to move. Now it turns out that he wasn't entirely wrong, but he wasn't entirely right. All these things are also forces too, as well. Oh, wrong one. Need to give you this. No. Okay, so moving on. Now we got Galileo. Galileo came along and said, actually, we don't need any forces at all to cause motion. All objects would be in motion all the time if we eliminated friction. The only reason they're not in motion is because of friction. It says right here, if friction could be eliminated, objects would be moving all the time. So that was Galileo. He said objects move all the time. It's their natural state, except friction causes them not to be moving. Neither of them were exactly right, but this guy put it together for us all and became known as the father of physics. He developed 3 laws of motion. We'll talk extensively about those this unit. The law of universal gravitation. It's the law of gravitation that is the same throughout the entire universe, which is why we call it the universal law of gravitation. He also developed the electromagnetic spectrum, the electromagnetic color spectrum. That's the Roy G. Biv, where you got red, orange, yellow, all the way over to indigo. And then, we won't cover this, but he also developed calculus for those people that are math inclined. So he did a lot of cool things. The most relevant for our purposes in this unit is the 3 laws of motion, and then on a smaller level, the law of universal gravitation. So please make sure you note these 3 things on a lesser scale, that one. All right, moving on. Okay, so a net force is the sum. This Greek letter right here, epsilon, means sum. So this you'll see in front of the capital letter F sometimes for the sum of the forces. So the sum of all forces acting on an object is the net force. When we say the word sum, mathematically we mean what? What operation? Adding, right? So mathematically we mean adding. Just remember though, when you're adding vectors, there are 2 important factors: the magnitude and the direction. So we're not just adding 75 and 125 here, right? We're not just adding 75 and 125. We're adding the numbers and the direction. So in terms of this direction here, what is this 125? A positive or a negative? Negative, right? Should be negative. And in terms of 75, should be positive. So if we want the net force, we take the sum of those 2 numbers, keeping in mind that 75 is positive, 125 is negative. So if you have negative 125 plus 75, what is your net force? Negative 50, right? And that's how you do net forces. Does that make sense? It doesn't? Just add them, sum. Okay. So now let's talk about balanced versus unbalanced. The easiest way to analogize this is think of it in terms of an arm wrestling match. 3 possible outcomes from an arm wrestling match. You can have the person on the right win, the person on the left win, or they tie, right? They're both applying a force. The person on the right applies the force to the left, the person on the left applies the force to the right. Whoever applies the most force is going to force the other person's arm to move in the direction that they apply the force, and they will win the match, right? So if both participants apply the exact same amount of force in the opposite direction, nobody moves. Nobody moves, nobody wins, right? So it takes an unbalanced force to move the opponent. So the balanced force is equal in magnitude, opposite in direction, right? Equal in magnitude, so the size of the forces are the same, but they're applied in opposite directions. So a balanced force, by definition, is a force that is equal in magnitude and opposite in direction. An unbalanced force is still opposite in direction, but not equal in magnitude. One is bigger than the other. It's unbalanced. Comprende? Alrighty, moving on. So that brings us to Newton's first law. It's called the law of inertia. You will be asked to know it by its name, not just Newton's first law, the law of inertia. The law of inertia. It states that objects in motion remain in motion and objects at rest stay at rest. But we added to this definition, objects in motion at constant velocity. This is important so you understand that when we talk about objects that are in motion, they are in motion at constant velocity. They are on cruise control. They are not accelerating. So an object that is in motion at constant velocity will stay at that velocity unless it's acted upon by an unbalanced force. An object that's at rest will stay at rest unless something forces it. If I put this in my own words, I'd say basically objects keep doing what they're doing unless they're forced to change their motion, which is acceleration. Remember, forces cause acceleration. So unless the object is acted upon by, and here's that key, an unbalanced force. Not just a force. I hear a lot of students always saying that. Unless acted upon by a force. Because if I act upon this with a force in this direction and a force in this direction that are exactly the same force but opposite in direction, so they are balanced forces, it doesn't move. It's only when it's acted upon by an unbalanced force that it moves. So that's a key word there. It's an unbalanced force, not just a force. It requires an unbalanced force. One that is not canceled out by any other forces. Okay. Write that in your own words. Again, my words would be something along, they're lazy. Objects do what they're doing unless you force them to change. Same as students most of the time, right? Keep doing what you're doing unless I force you to change. My son keeps wearing the same clothes unless I force him to change. Alright, so let's talk about inertia. Inertia is an object's resistance to change in its state of motion. Literally in the Latin, inertia means lazy or lacking skill. So objects are lazy because they have inertia. It's a resistance to change in motion. Mass is the unit or the amount of inertia that an object possesses. Its units are grams, kilograms, and milligrams. So when we talk about mass, we're talking about an object's inertia, not its weight. There's a big misconception that students have that mass and weight are the same thing, and they are not. Mass is completely different than weight. Mass measures an object's resistance to change. The more massive an object is, the more resistant to changing its motion that it is. It will either stay at rest or it will stay at a constant velocity unless it's acted upon by a huge force. The bigger the mass, the bigger the force that it takes to cause it to change its motion because of its inertia, not because of its weight. Because weight can change. Right? If I take you to the moon, all of a sudden you just went on the best diet in the world. You're down to 1/6 of your body weight. But unfortunately, your mass is still going to be the same. You're still going to be difficult to move because your mass and therefore your inertia does not change. Okay, so let's name an object that has a lot of inertia. The sun. I heard the sun, right? That's exactly what we said. The sun, Jupiter, Betelgeuse, which is apparently a star. So yes, those things are very, very massive. They're very, very massive, which is why they stay right at the center of the universe and they don't move because they're massive. The Earth is less massive, but yes, A train, very massive also, in terms of things on Earth. What about an object that has a really, really small amount of inertia? A bug, a piece of paper, maybe. How about protons, neutrons, electrons? Right? Really, really small. And of these, electrons have the smallest amount of mass. And then supposedly they've got these subdivisions now called quarks that are what protons and neutrons are made of. So how about an object that has a small amount of inertia but a really large volume? We want to differentiate between inertia and volume. What's an object that's easy to move that's really, really big? Yes. An inflatable pool. Before you put the water in it, I assume. Okay. He's on the right track. What's some other things? Yeah. A car would be easy to move? Well, I think a balloon. I heard there we go. A balloon. And then here's a Goodyear blimp, which is one of the biggest balloons that I think I've ever seen. So yeah, a balloon. They're because they're full of hot air, right? So they're easy to move, but they're very, very, very large in terms of volume. So don't get confused between something having volume and having mass. Right? It can have a lot of volume, but a low mass. Well, how about something that has a very small volume, but a lot of inertia?
Weights.
Lead weights. Okay. Yeah. We went with the most massive thing in the universe in terms of its size, which is what's called a neutron star. It's hypothetically, because we haven't never proved this, but it's hypothetically a star right before it explodes and turns into a black hole, which of course you know is the most massive, supposedly so massive it can't even let light get out, blah blah blah. So this is a very, very massive but a very, very small region in space for relative to its mass. Okay, here's the question that we've been leading up to. Can you lift / move / pull the space shuttle in space? But before we do that, to save us from any Weisenheimers, can you lift / pull / move the space shuttle here on Earth? Let's just get that out there. No, nobody can. We're not talking about Superman. Can you do it in space? I heard yes. Tell me why you think you can do it in space. Because it weighs less. It's actually weightless in space, right? Is she right?
Yes.
Anybody want to disagree with her? Okay, so how do we define an object's resistance to change in motion? There you go. So don't be so shy then. The mass is still the same. And remember, mass is its inertia. Inertia is resistance to change in motion. Just because its weight changes doesn't mean that its inertia changes, because its mass is the same. It will be equally as hard to move in space as it will be here on Earth, because its mass is the same. Remember I said the moon? You're equally as hard to move on the moon as you are here, because your mass is the same, which means your inertia is the same. Resistance to change in motion, which is measured, which is mass. It's the mass. So mass does not change. It's just the effect that gravity has on your mass that causes you to have weight. Okay, so the answer is a big fat no. And the reason is it's weightless, but it still has inertia. It still has the same amount of inertia. Which is why we talk in terms of mass, not in terms of weight, because weight can change. Mass cannot. It's universally the same everywhere you go. Okay, we're going to do this one last slide, which is a bunch of demos that we will do for you in class, and I will not be adding to the video because don't have a camera for that. But so I'm going to put the video on stop, and we will pick these notes up during the next class.